Now, first things first, let's talk about the exam on Wednesday. So exam 1 on Wednesday, as in this upcoming Wednesday, which is 0203, in room AH355 at what time, sir? 1:45 p.m. So that's Ayers Hall at 1:45. The exam will open at 1:45 and will close a couple hours later, right? And if you take it anywhere but in that room, then your score will not count. You'll have a 0. So you have to make sure you're there. If there's any reason you think you won't be able to be, like a legitimate reason, you know, obviously lots of legitimate reasons, like the most currently relevant one is
okay, what class is it?
Oh, I'm gonna mute you. Okay. Currently relevant one is if you have to quarantine or something like that. So normally, I just want to make this clear. If you miss a class, like even an in-person class, and you tell me you're sick or something like that, I'm usually not strict about that. I'll just be like, okay, I just believe you, and then I'll mark you as absent excused, right? But for an exam, if you miss it, you got to let me know ahead of time. Of course, barring any emergencies, right? Like you can't plan for emergencies, but as soon as you can, if you think you're going to miss it or you do miss it, as soon as you can, let me know, and you will have to provide an excuse. So most of the time I don't care, but for exam days, you have to provide an excuse, and you don't want to miss the exam if possible, okay? Because like if I have to go make a makeup exam, my exams are easy. Just going to go ahead and tell you my exams are easy. And if I have to make a makeup exam, I have less easy problems to pull from in WebAssign. Oh, thank you for whoever spotlighted me. So just, if possible, don't miss the exam. Okay, let me get attendance updated. Who came in? Let's see. I've got 1, 2, 3, 4. Okay, just Bailey, and I think the other 3. So I'm missing Robert, Catlin, and Jace. All right. Okay. We left off talking about, oh wait, sorry, one more thing about exams. I don't think I've been doing a great job keeping up with review problems for you to, like, problems from the back of each section to mark for review in addition to your WebAssign problems. So here are some that you'll want to look at. These are in addition to, now some of them will be very similar to what you've got on WebAssign, of course, but just some extra practice from the 4 sections that exam 1 is covering. And remember that I did describe earlier that exam 1 is only covering these 4 instead of all 6, right? I've already talked about that. Instead of all the way to 5.5 and 5.6, exam 1 is just covering these 4 sections. And the exam will be, I believe, 10 questions. Actually, I forgot. I just looked at it, but I forgot. It's like somewhere around 10 questions, maybe a dozen questions. Okay. So now we're ready to get back into actual lecture, like what we were doing, which was inverse trig functions. We were finding the exact, oh wait, where are we? We were evaluating inverse trig functions. So just quickly recall that if sine of theta is equal to x, then that means with restricted domains, we can write sine inverse of some number. So this is not an angle. Being inputted into the trig function is, inverse trig function is not an angle. It outputs an angle. Does the opposite of what this one does, right? Of course, there's similar setups for all 3 trig functions. And we had to note, I went on an hour-long lecture about the domains and ranges of these things and how we had to restrict the domain of the sine, cosine, and tangent functions in order for the range of the inverse functions to be appropriate to be where we want them to be, so that they still act as functions. Okay. And those domains, no, sorry, the ranges were, so these are, I'm now going to write ranges, you know, I'll tell you what, I'm going to do it over here. Ranges of inverse trig functions. I drew pictures for each one, but for this one, I'll just tell you what they are as intervals. For the inverse sine function, it was that negative pi on 2 to pi on 2. So that's from that negative y-axis. I will go ahead and draw it. It's not that hard to draw it. From here to here. Negative pi on 2 is this angle, and then pi on 2 is up here. Cosine inverse of x was a little different. It was 0 to pi. And remember, these restrictions are just to make sure that we're not doubling any values. It's like the same way that you would have to restrict a square root thing to make it a function. You've got to get rid of all the negative outputs. Here, since these trig functions are cyclical in nature, they can get, for tons of different inputs, they can give the same outputs because of how it, if you just do the same angle but a full rotation away, there's tons of repetition happening, right? So we had to restrict that to make sure that when we invert the functions that they still act as functions. Tangent inverse of x acted kind of the same as sine, except you just cannot include those endpoints. Because we know that that the tangent function, remember the original tangent function, its domain did not allow for us to plug in these values. So hence, that's why the range of the inverse tangent function does not allow for you to output those values. That's why there's parentheses instead of brackets. And that picture would look like, I would just draw some open dots there just to emphasize that those 2 points are not being included. All right, so we're in the middle of example such and such. What was it? 4. No, oh wait, no, we were on example 1. That's right, because I spent so much time last time talking about domains and ranges. So example 1 continued. I believe we left off with d cosine inverse of negative square root of 2 over 2. Oof, okay. Yes, I believe that's where we left off. Let me check. Oh yeah, there's only, okay. Okay, cosine inverse of negative square root of 2 over 2. We know we're looking for an angle. We know that cosine is going to, when does the cosine function output a negative? When it's in the, when x is negative, right? When it's in the first or, no, the second or third quadrant. So we know we're somewhere over there. And we know that the square root of 2 over 2 yields a certain type of angle, right? So let me see. I'm sorry. I'm trying to remember how much detail I gave you here. How did we go about solving this? I'm trying to remember how much stuff I just pushed under the table, swept under the rug. Let me just write down the stuff I'm noting. Note that cosine theta is negative in quadrants 2 and quadrant 3. So we expect theta, which is what we're looking for, right? This thing outputs a theta to be in one of those quadrants. Oh, one of those quadrants. Okay, so that's helpful. We also know, though, oh God, my voice is probably going to crack a lot. I'm like, Mondays and Wednesdays I teach a lot, and in the morning, and my voice is going. We also know that cosine inverse has an output range of 0 to pi. 0 to pi. So since the range of cosine inverse, which I could write like this, I could say that cosine inverse ranges between, it's just another way of writing that interval up here. I could say it in words. I could say the range of cosine inverse is 0 to pi, or I can just say it all together here. This kind of says that same thing, I'll just compact it. The bounds of cosine inverse are 0 to pi. Since this is true, then theta, and remember this thing is equal to theta, right? Cosine inverse is equal to theta. Okay. Then theta must be in quadrant 2, not 3, right? Not 3, because quadrant 3 is outside the range here. Quadrant 3, here's 0 to pi where cosine inverse is allowed to output, but quadrant 3 is down here. All right. So that means that we're looking for an angle in quadrant 2. Now we need to remember what kind of angle gives a, so in other words, we're saying now what angle theta gives cosine of theta is equal to negative square root of 2 over 2. And this is where it's helpful to just start to like remember what types of angles give this form, right? This form of output, square root of 2 over 2. You can draw your reference triangles to help you remember, but hopefully this is looking familiar. You're thinking it's a pi on 4. So you should recognize this. So we should start to recognize, the form root 2 over 2 as an output from some pi on 4 or 45-degree angle. But which pi on 4 angle lives in the second quadrant? So this is where we're almost there. We know the angle is in quadrant 2. We know it's a pi on 4 angle. So a pi on 4 angle, that's, you know, the ones that cut right down the middle, like a 45-degree. But if it's all the way over here in the second quadrant, this is 1 pi on 4 here. Then another one would be 2 pi on 4. And then this one would be 3 pi on 4. There it is. Theta is going to be equal to 3 pi on 4. In other words, cosine inverse of negative square root of 2 over 2 is equal to 3 pi over 4. All right. It's really helpful if you start to recognize these outputs. Anytime you see a square root of 2 over 2, you're looking at a 45-degree or a pi on 4 angle. Anytime you see square roots of 3, like square root of 3 over 2 or 1 over square root of 3, square root of 3 over 1, then you're looking at either a pi on 6 or a pi on 3 angle, a 30 or a 60-degree angle. That kind of lets you know what kind of reference triangle you're working in. Now, notice I didn't draw the reference triangle here because I didn't really need to, right? The more comfortable you get with these angles giving these kinds of outputs, the easier these are going to be, and the less detail you're going to need, the less detail you feel you're going to need to be able to solve something like this. All right, let's do E. Are there any questions about that? I think I may have solved that a little differently than last time, but I don't have my notes from last time. So, any questions? I hope I didn't confuse anybody. Just let me know. I'm gonna write down example E, but let me know if you've got any questions. All right. Tangent inverse of -1. Tangent inverse of -1. I'm going to go a bit faster now. When does tangent output a 1 or a -1? When does tangent Well, what kind of triangle? So if I drew them quickly, I could have the 1 square root of 3 and 2. This is a 60 degree or a pi on 3, right? That's a pi on 3 angle there. I could have the pi on 6, which is really just this one rotated, right? So there's the 30 degree, that's pi on 6. Or I could have the 45, 45, 90. Of course, these are all right triangles, by the way. There we go. With the 2, 2, and square root of 2. No, oh no, sorry, that's what I meant is square root of 2, square root of 2, and 2. Sorry, I was going too fast there. And that's the 45 degree. All right, now I also know that tangent of theta is equal to opposite over adjacent. Adjacent, opposite over adjacent. Which of these triangles has a ratio of 2 sides that yield a 1? It's got to be this one, right? Opposite over adjacent, same over same, that's going to be an output of 1 there, right? So we are looking for, again, another pi on 4 angle, a pi on 4 angle. Maybe it's pi on 4, maybe it's 3 pi on 4, 5 pi on 4. How do we know? Well, we're looking for a negative one, right? So when does tangent output a negative? When is tangent negative? And in fact, let's not even bother with the entire picture of where tangent's negative. Let's just say when is tangent negative in those 2 quadrants that we're allowed to be in for the output of tangent inverse here. So tangent is negative in either quadrant 2 or quadrant 4. Yes, sorry, quadrant 2 or quadrant 4. But we're only allowed to output in quadrant 1 or 4, so it's got to be in quadrant 4. So when is tangent negative? Quadrant 2 or 4, but we know because of the range that we're going to want quadrant 4. So this is because of range of tangent inverse. Okay, what is the pi on 4 or the 45 degree angle? I'm going to go with the radian version. What is the pi on 4 angle that's in quadrant 4? Okay. Maybe you already know, but so this would be 1 here. That would be 1 pi on 4. 2 pi on 4 would be the, pi on 2 right there on the axis. And then the 3 pi on 4, 4 pi on 4, which of course would just be pi, and then 5 pi on 4, 6 pi on 4, which would be this 3 pi over 2 axis here. And then, of course, 7 pi on 4 is what we're looking for. There it is, 7 pi on 4. So that means theta is 7 pi on 4. In other words, tangent inverse of -1 is 7 pi on 4. These mean the same thing because tangent inverse of a number is an angle. Okay. Example 2. Calculator approximations. This is easy. So what if I ask you, tangent inverse or approximations or sine inverse or cosine inverse of some number that you don't recognize, like it's not a 1 or a square root of 3 or a square root of 2 over 2 or a 1/2. It's none of those nice outputs that we're used to from our reference triangles. What if I said something like, what is sine inverse of 0.71? What do you do with that? Like, what the heck is that? Oh, well, all you do is you plug it into the calculator, and let's go to 5 decimal places. Go to your calculator, make sure you're in radian mode. Well, actually, it doesn't matter. I'll write both. The question will tell you what it wants. So you go to your calculator. Hopefully you know how to get to your inverse sine. What am I doing? Yeah, inverse sine function. So in degrees, I'm getting sine inverse of 0.71 is equal to 45.23492. 23491, but then we round up because of that 5 behind the 1. So 23492. That's it. That's in degrees. Okay, that's in degrees. Oh, and I should say approximately, since we're approximating. Shouldn't say equal, I should say approximately. And by the way, if I wanted that in radian mode, of course, sorry, I'm using the Windows, the calculator that Windows provides. I probably should not do that. Okay, but in radian mode, it's 0.789 498, but we would round, so 50 with the appropriate rounding. And this is, of course, in radians. All right, so nothing really to say about this, except make sure you note what, if you're supposed to do it in degrees or radians, so what form the answer is supposed to be in, and also make sure you know how to round, right? Make sure you know how to round. Part B, let's do sine inverse of 2. Plug that into the calculator and see what it says. It messes up, right? It says, what are you doing? That's undefined, because recall that the domain of sine inverse of x, so the input, the domain, is bounded between, I wrote this down for you last time, -1 and 1. That's the domain of the inverse sine function. Thus, this problem has no solution, so this is undefined. Because I'm asking you to put in something that's, doesn't make sense. It'd be like if I gave you a function 1 over x and say evaluate it at 0. You would say, well, I can't. It's undefined. It's outside of the domain. Okay, that's all I got for that one. Only thing to take away from this really is make sure you know how to use your calculator. And even if you forget this business about the domain, your calculator is going to tell you, right? Even if I give you a test question that says find cosine inverse of 5, you plug it in, your calculator is going to say, nope, that's undefined. And then you'll be like, oh yeah, that's right. And then you just say undefined. Now remember, tangent does not act that way. Tangent inverse's domain is not bounded. So just keep that in mind. It's only sine and cosine that have those really small little domains for their inverse functions. Let's apply some of what we've been doing here to some pictures. Let's apply it to some pictures. Find the angle theta. Let's say in degrees rounded to 1 decimal. And I've got to give you a picture here. Oof, okay, there's theta. It's a right triangle. 24 and 20. Okay, I'll give you guys a second, and then I'm going to ask someone what trig function would you use to find theta? So Karina, what trig function would you use in this case to find theta? Anybody else have any ideas? What trig function would we use given this side and this side of a right triangle? Oh, wait, sorry. Someone, I just saw the chat. That may be Karina. Yes. Okay. No, Braden said sine. And why are we going to use sine? Because we are given the opposite side and the hypotenuse. Relative to theta, we are given the opposite and the hypotenuse. And what trig function deals with those sides of a right triangle? It's the sine function. So opposite. So recalling, oops, that sine is equal to opposite over hypotenuse. So in this case, sine of theta is, of course, 20 over 24, which real quick, let's just reduce that because it's a fraction that can be reduced. It's 5 over 6, right? But I want theta, right? I want theta out of this. I want the angle. How do I find the angle? Well, that's what the inverse trig function is for. Theta, take the inverse sign on both sides. It cancels out the sine function. And I say theta is equal to sine inverse of 5/6. 5 over 6. Real quick, let me write out what I mean by that, taking inverse sine on both sides. Like explicitly, this is what's happening. If sine theta is equal to 5 over 6, I'm going to take that inverse on both sides. Like imagine I had an equation that said x squared equals whatever, 4. Then how do you undo the function x squared? You use the inverse, which is the square root, right? So you take a square root on both sides. That's all that's happening here, except the inverse of sine is just written like this. So what happens here is sine inverse and sine cancel as functions, just leaving me with theta. So that's what's happening there. Just in case that wasn't clear about inverse function and the base function canceling there. So now I'm left with this problem. Is this a familiar ratio? No, this is not a familiar ratio. Like, what are some familiar ratios? Like, square root of 2 over 2 or square root of 3 over 2. Those nice things that we're used to seeing. Well, relative, you can argue that they're not nice, but just a 2. Wait, no, sorry, not 2. Okay, I'm crazy. Well, wait. Yeah, not 2. Stuff that looks kind of like this, or 0. 0, of course, could be one of them. It's not a familiar ratio. 5 over 6. What does that mean? That means we use the calculator. So we go over to the calculator. We say 5 divided by 6. Oh, make sure your calculator's in degree mode because it asks for the angle in degrees. Go to my trig, hit sine inverse, and I'm getting theta is 56.4 degrees. Rounded to the 10th place, 1 decimal. Good. All right. Another one. But I'm going to insist that you find it in 3 different ways. And I'll show you what I mean by that. Basically, I mean 3 different trig functions. And here is the triangle. Same triangle. Side 24, side 20, theta. Here's what I want. I want set up as theta is equal to sine inverse of something. Now, I already told you it's 5 over 6. That was example 3, right? So that's done. That's just opposite over hypotenuse and simplified the fraction. I also want to know what would it be if I insisted that we use cosine? What would it be if I insisted that we use tangent? Why would I do that? Well, I don't know. It depends on the problem, right? Okay. Now, what's the issue here? The issue is I don't know the adjacent side, and cosine and tangent involve the adjacent side, right? That's the adjacent over hypotenuse and opposite over hypotenuse. How do I find the adjacent side? So since cosine and tangent cosine and tangent involve the adjacent side, let's find it. $20 squared plus, I need a name for it, I'll just call it b squared, so this side is b temporarily, is 24 squared. See what I'm doing, right? Pythagorean theorem. I'm just going to go ahead and calculate it. I'm getting 176. I don't want this as a decimal, right? So I'm getting b is equal to the square root of 176. You may have a nice calculator that simplifies this for you, but I'm going to do it the old school way, which is to try to find a perfect square factor inside of 176. I believe, doesn't 16 go into it? I can ask, yes, calculator says yes, so this is the same as that, which of course gives me that. Finally, a nice clean exact answer here. B is 4 times square root of 11. All right. So the cosine of theta then is going to be adjacent over hypotenuse. So 4 square root of 11 over hypotenuse 24, which by the way reduces. So cosine of theta is going to be, the 4 can cancel, leaving me with just root 11 over 6. That means the cosine so theta is equal to the cosine inverse of square root of 11 over 6. Tangent theta is opposite over adjacent, so I'm getting 20 over 4 square root of 11, which again reduces just because it's a nice fraction that has some common terms. I'm getting 5 over square root of 11, canceling the 4 out, and there we go. So that means that if I solved for theta, the input of my tangent inverse function would be 5 over root 11. All right. So this is kind of the culmination of all the inverse trig function like stuff. Kind of seeing how it can be useful to solve a triangle, and also how if you insist on using a particular trig function, you may have to solve for the missing side on the right triangle. So are there any questions about that? Because that's kind of like, this is kind of one of the big problems. Okay. Example 5. So yes, not I almost said yesterday. Wednesday was all bunch of setup, and today is a bunch of examples. And I'm hoping we get done early so that we can talk about reviewing, or to see if you guys have any questions from earlier in the semester. Oh, Braden said, can you keep a root in the bottom? If you don't like that, you can. So the answer is you can, but look out for if the problem, if it's a WebAssign problem and it says rationalize any denominators, watch out for that. So if you did want to do that real quick, we can just to have it written down. And of course, he's talking about the tangent one. You would say that's 5 square roots of 11 over 11. There you go. So you could replace this there. Yep. Okay, here comes a weird problem. Find all angles between 0 and 180, or 0 degrees and 180 degrees, or I could say 0 to pi, that satisfy satisfying the equation and round to 1 decimal place. What's the equation? Okay. So how do we find the angle? Well, that's, just a matter of saying theta is equal to sine inverse of 7/8. And we can use the calculator, but here is where things are going to get a little weird because it says find all angles, and there is more than one angle that satisfies this equation. And you might tell me, well, yeah, I know that. That's why we did all of that work, restricting the range of these things so that we didn't have to deal with the weirdness where you get, more than one angle. And the whole point of all that was to keep this thing as a function, right? Because if your function is outputting two different outputs, then it's not a function, right? If you give it this one input and it yields two outputs, it's not a function. But it specifically is giving us an equation. We are not treating this as a function for this particular problem. When you're dealing with triangles, like the two examples we just did, you only want one output for the triangle, right? Because it's a picture. There's only one angle, right, for the triangle. Well, there's only one theta in that case, right? So that's when you're dealing with a function. Here it's saying equation. As an analog, so we need to just take like a detour and just consider equation versus function. Equations can give you two outputs. For example, if I said, just as an equation, x squared is equal to 4, then what would you guys tell me the solution is? You would say x is plus or minus 2. Two outputs for the same input, sort of, right? If we think about it like that, it's not a function, right? Okay. Whereas with a function, so this is equation, so the equation can have multiple solutions. Okay, now a function cannot. So what is the analog for this kind of thing with a function? If I say f of, wait. Sorry, what am I trying to say here? Yeah, that's fine. F of x is equal to square root of x, which by the way is the operation I use to solve this equation, right? Square roots on both sides. So if I square root x and I'm letting x be 4, which is exactly what happens over here. Well, its input is 4. It's like I'm square rooting the 4, right? It's not the same x necessarily. But the point is that I'm taking a square root of 4 in this function, right? Then f of 4 is square root of 4, and I would just say 2, just the positive, only the positive, right? Because we all agree that the square root as a function can only output one value, and we all agree that it should be the positive one, only the positive one. That's why if you look at a picture of this graph, it's not a complete sideways parabola, it's just the top half of it, right? We agree collectively that if we're talking about a square root as a function, we only take the positive values. We restrict its range, just like with the trig functions. In an equation, we say, oh yeah, you can do whatever the heck you want. Like over here in the equation, you can have those multiple solutions. Same thing going on up here with the trig functions. Sorry, the trig equation, right? This is a trig equation. We are now allowing you to open that range back up because we're not considering it as a function and tell me every angle that can be outputted from this. But that would be infinitely many actually for a trig function because of the trig equation because of the way they act, but we're restricting between 0 and 180. Okay, so hopefully that kind of made sense here, equation versus function. This is something no one actually ever explicitly explained to me. And I remember getting really confused when I went back after these lectures in my trig class and going, well, why are there two solutions? Why are there sometimes two solutions for stuff like this when we agreed there would only be one to make it a function, right? It's because in this, we're not dealing with a function. Sometimes you may catch me calling it a function because I'm just being like informal, but technically we're not dealing with a function at this point. So I'm going to rewrite the equation just to get it back up here. And theta is sine inverse. Now, again, this is, as I said last time with the last problem, this is not a nice angle that we recognize, so we're just going to go ahead and plug that into the calculator. We'll round to 1 decimal place, but we will not be out of the woods until we find that other angle. So I'm getting 61.0 degrees. Is there another angle? In 0 to 180? Well, consider that sine is positive in 0 to 180 in quadrants 1 and quadrant 2. And since that describes 0 to 180, we know that there will be another angle somewhere in the second quadrant that yields something like this. So as a picture here to help us see what I'm talking about. Consider that sine of theta equals 7/8. If I drew theta, this is describing the opposite side over the hypotenuse. So the opposite side is like length 7, and the hypotenuse is length 8. So it's a pretty, steep looking thing here. It would be even steeper, but I'm drawing it like this so we can still see theta in there. Okay, so I don't know what the adjacent side is. I don't care. That's not the point here. So I just found that one, 61 degrees. Actually, that's a pretty good drawing, I guess, 61 degrees. But I know that since sine is also positive in quadrant 2, which by the way is still in that range of 0 to 180, that it can give me another theta over here, like a symmetric one over here, where this side is still 7 and this side is still 8, right? They're both still positive because this side is like a y-axis or a y value. It's like a height, and it's still positive in quadrant 2. Now, if this was negative, then we'd be in trouble, right? Because sine is negative down here, and there would be no solutions in the 0 to 180. Okay, so what is this angle then? What is this angle all the way over here? So the question is, what is that other angle? Well, since they're both happening in the 180 range, 0 to 180, I can just take, so what I'm asking, when I say the other angle, let me try to draw it for you here. It's coming from the x-axis all the way to the hypotenuse there, as I drew it there. So hopefully you can see that from x-axis to this line. So that's the angle I'm looking for. And just based off of the geometry of the situation here, your intuition is probably telling you you're going to do this. You're just going to take 61, your original angle, from that 180 to get the other angle, which is 119. That's one of the trickiest problems probably that we will talk about. Given an equation, so not a triangle, right? Like it's similar, but I'm not giving you a triangle. I'm giving you an equation and telling you to solve it. And there's potential for it to have more than one solution depending on the the range of the degrees they're giving you here. So I said this a second ago, but let's note something. Let's note that if the equation was sine of theta equals -7/8, so in other words, in quadrants down here, 3 and 4, then there is no theta in that range they gave, 0 to 180, that solves the equation, because sine can only be negative down here, and 0 to 180 is up here. That solves the equation. So it's not that there will always be two. It really depends on that range of angles they give you. So in this case, there were 2. Sometimes there will only be 1. Sometimes there will be 0. It just all depends on what they give. Let's practice it a bit more. I'll leave that there for a moment in case you need it. I'm going to say same instructions as example 5. So that means same range. So, you know, theta is between 0 and 180. Right? Sorry, I feel my voice going. So cosine of theta is -1/3. Oh, I've been real lax about putting parentheses around the input of theta in my sine equations and sine functions. Sorry about that, but I've explicitly written it there. Remember, I said at the top of this class this, you know, it's, if you really want to, you could always write them to explicitly explain that that's the input. But when it's just the theta, I mean, it's pretty clear that theta is the input of cosine. But all right. Okay. What are we thinking? What are we thinking here? Well, we want cosine theta equals -1/3. That's if we're solving for theta, we're going to take the cosine inverse on both sides. Is this a nice clean angle like 45, 60, 30, 90, 0, one of those? No, it's not. It's close, right? It's almost, if just throw a square root over that 3 and it would be one of those nice angles we're used to seeing, but not the case. So bust out the calculator and we'll get theta is approximately 109.5 degrees. So that's what I wrote down. Let me make sure. 1 divided by 3, negate it. Cosine inverse. Yes, okay, 109.5, good. All right, is there another angle? This is where you stop and you say, is there another angle? Well, here's how to phrase the question. Is there another angle in the bounds that they gave in the problem, which I said 0 to 180, where cosine can output a negative? No. Right? No. Why? Well, because 0 to 180 describes quadrants 1 and 2, but cosine is only negative in quadrant 2, and we already got that one, right? So we're done. So that's it for this. Well, I mean, for this problem. So there's only one. There's only one this time, because cosine cannot output negatives in twice in this region they described. Okay. Unlike back here, where can sine output a positive twice in this range that they gave? Yes, in quadrant 1 and 2. Can cosine output a negative twice in this range? No, only in quadrant 2. If we extended the range to now include quadrant 3, like if I said 0 to 270, then we would be, then there would be another angle. We'd have to find it. Probably draw a picture to help us with the geometry to figure out how to find it, right? But in this case, that's it. So weird. So the answer is just that. All right. Does that make sense? Does anyone have any questions about that? I can probably build another one if you would like to see another one. I'll give you a second to think about that. example 7. Here's a little fun with some inverse trig functions. Find the exact value of each expression. Cosine of sine inverse of 35 over 37. And B is cosine theta of 12 over 37. So that first one looks kind of scary, maybe. But all it is it's saying, remember that the sine inverse, or a trig inverse, like sine inverse, cosine inverse, or tangent inverse of some, ratio or number, this whole thing just describes an angle. So all I have to do is figure out this, which will give me an angle. I'll find that angle, which will be, a number, some angle, and then I'll just plug that into cosine. That's it. Okay. So what is sine inverse of 35 over 37? Ooh, actually, no. The way I described it's actually not the way we're going to solve it. Sorry. What's the way we're going to solve it? I mean, that's the right interpretation, but how about this? Instead of actually getting this as, because they told us to find the exact value. That's the problem. We could plug this into the calculator and get some, some number. But they want the exact value. So how about consider that this helps us describe a triangle, right? This thing, if theta is equal to sine inverse of 35 over 37, then that means that sine of theta is equal to 35 over 37. But that describes like an opposite side and a hypotenuse. Okay, and then here's theta. I don't know theta, but that's okay. Because now if I have a picture and what I want is cosine of theta, what's cosine of theta here? It's going to be adjacent over hypotenuse. So all I need to do is find this adjacent side and I'll have cosine theta. So the point is you build a triangle from this interior part. Build the triangle and then you replace the whole interior inverse trig thing with just a theta. And then once you write that down, hopefully you see, oh yeah, I just need to, cosine of theta is adjacent over hypotenuse, so I just need to find this missing side. So I'll say, Pythagorean theorem, 35 squared. I'm just going to say ... I believe it ends up being a whole 12. Yeah. Okay. So that means cosine of theta then is adjacent over hypotenuse, 12 over 37. But that means that cosine of sine inverse of 35 over 37 is just 12 over 37. There we go. Now part B. Oh. Wow, I just got so mixed up in my notes. Never mind, there is no part B. That's just the second step that I was writing down. Wow, that was dumb. Sorry. So we're just solving this. Find the exact value of this expression. In fact, why not? Let's just do another one because I gave you a part A. Normally, when I write my notes for this class, I don't actually solve the problems. But in this one, I've for whatever reason, felt it necessary to write it out and solve it. And I just, without really reading what was going on, I thought that was the second part to the example, when it was really just the second step of the first part. But how about this? How about tangent of cosine inverse of 12 over 37? We've kind of done the work already to set this up. how would you start from scratch with this though? You would draw your triangle. You would say, okay, adjacent over hypotenuse, 12 over 37. You'd say tangent of, theta, right? So tangent of theta, where this thing, this whole inverse thing is theta. So I'm got tangent of theta is equal to opposite, right? Opposite over adjacent. I don't have the opposite side, so you would take your Pythagorean theorem over on the side, let's say a squared, just to, okay, and you would find a to be 35, and then you'd say, okay, I got my opposite side now, so tangent of theta, which by the way, this entire ugly thing here is theta, is just going to be 35 over 12. And this means that tangent of cosine inverse, because that this inverse trig thing and theta are one and the same, so there we go. Sorry about that little mix up there with A and B. Oh. All right, that finishes section 5.4. That finishes chapter 5 for us. So, what have y'all got for questions? We have 30 minutes left, so if you want to go open up your WebAssign and look at some questions, if you want to look at the questions I gave you at the top of this lecture to mark for review, you can go look at those real quick. Remember, you can get your ebook open through WebAssign to look at those. Those questions are at the back of each section. So let me know. We got 30 minutes. You got 30 minutes with me to just ask about anything you want, well, relating to trig.